Good morning, everyone. Good morning. We're all used to seeing this iconic architecture, a simple service with a back-end database. It's kind of what we're constantly writing when we're in this microservices type world. And when we design these systems, we often are very focused on performance and how they're going to behave. We tune them, we expect something like this, where the typical load will be well below what our max supported is, and therefore we'll be able to handle everything that comes in. But there are cases where our load will increase. It'll rise up, hopefully staying below that max limit, and we'll do what's kind of natural and standard, and what we hopefully our systems are going to be able to do, which is we'll add another instance, we'll scale out, we'll be able to reduce the load on each of the individual systems, and we've kind of increased that maximum supported load. This would be the ideal situation. But that's not always an option. There are probably going to be cases where our system looks like this, where we get a sudden influx of load that crosses our max supported value. And what's worse is once it crosses that line, it starts growing at a rate that we only ever want to see inside of our 401k. The number of requests coming in just continue to cumulatively compound new requests on top of requests that fail that are still stalled out in the system. And we're going to have a bad time. Now, some people think that this hardly ever happens, that it's probably something we don't necessarily need to handle because it's very rare occurrence. But there's a number of cases throughout the industry where sudden spikes in load outside of the typical expected values can suddenly happen, whether it's shopping or events that happen once every 4 years, like sporting events, or specific awards ceremonies, or maybe more frequently when those shows come out and we absolutely must watch them on the first day. And in our industry, we might think, well, yeah, we don't have quite as spectacular or newsworthy events such as these, but we do have a number of cases where the load will suddenly spike, and these events happen more frequently than we really want to expect. They might happen on a yearly basis, they might happen quarterly, monthly, daily, and sometimes even weekly. While we expect load to stay relatively stable, they will suddenly see a spike and we're going to have to deal with it. And you start to ask yourself, why can't we keep up? What's the bottleneck in the system? What's slowing us down? But you also need to be asking yourself, are you stable? Is your system staying up? Is it being able to handle and serve requests? Because what we want to do is prefer graceful degradation of our services over failures under load. We need to make sure not only are we handling it, but we're doing it in a stable manner. So a number of years ago, I was working on a system that looked like this. It was in a big data world, so we replaced the RDBMS system with a NoSQL, but we had lots of systems outside of our four walls pushing data into us through a Java REST service. Now, for a number of reasons, some of them functional, we decided that we needed to implement a queuing mechanism in between, something that would help us to land the data in one staging location and distribute it out to a lot of different systems. And what was interesting is that we now implemented a part of our system, we got a unique insight. We were actually able to measure how the system was behaving around that queuing mechanism. How many of the messages were doing when they were coming in versus how the messages were going out. Is there a difference between them? And what we actually saw, and what our clients started to complain about, was that we were developing this lag. We were not able to push the data out to that downstream NoSQL system as fast as the messages were actually coming in. And so it looked like our system was not able to keep up. And we now had to respond to that. We had to rely on the concepts and we had to rely on ourselves to be able to get ourselves out of this situation. And we started implementing a process, probably something that most of us all do. And I'm going to call that the L-ball process. It came about in 1952. L-ball is not someone who's well known in the realm of queuing theory or distributed systems and computing, but she is an influential individual who changed society as a whole. And if you're not really sure who L-ball is, maybe this will help. Now, before I get any jokes about me being old, I've only watched these in reruns, so I was not here when the episode actually came out. But one episode in particular left a lasting impression on me. It's an episode where Lucille Ball got a job handling chocolates, going down a conveyor belt, having to wrap them before they get down the path. Similar to what we have to do in computer systems of being able to handle requests before the next one comes along. Now, she was working at a reasonable rate, reasonable success scenario, but then, of course, life changes. Things get faster, and she now has to deal with them. And of course, if we use this relying on our computer system, we had alarms that started triggering, telling us that we were not able to keep up. And we did what was intuitive and natural, similar to what we do with the natural REST-based system, is we started to scale out. We added another worker who accompanied her, helping to wrap and keep up with the load. This should solve the problem, right? We should be completely happy. But things went a little awry. We were not able to keep up, and we started having to scramble. And specifically, similar to her, we started to fail in amusing ways, or spectacular ways, whichever way you want to look at it. What happened was while we were viewing our system as not being able to deliver and push data fast enough, we cranked it up, scaled out, and suddenly started making that downstream system unhealthy. We started to push data into it faster than it could keep up, and it tipped over and fell over in an unmanageable way, and we caused a brand new failure that we didn't even know about. Specifically, when we implemented that queuing mechanism, while it helped in our functional use cases and even helped reduce some of the back pressure that was happening to the client, we had actually unwittingly removed it from the entire system. We didn't know it was there and what purposes it was serving. We're thinking that it slowed us down. So by moving it and not paying attention to it and scaling up and just seeing how fast we can push the system, we cause downstream problems. So what is backpressure? It's a term we steal from the mechanical physical world, often talking about gases flowing through pipes, but it was kind of reinvigorated in the computer science field in 2014 as part of the Reactive Manifesto, where it talks about a series of components working together, and when one of those components fails to keep up, and it cannot absolutely fail, it must be able to communicate effectively to upstream components to kind of reduce the load. And so in our picture here, we had a backpressure mechanism without even realizing it. Most of every system you probably are implementing and deploying right now has backpressure in it, I guarantee it. But in this case, when the NoSQL system could not keep up, it slowed down writes. Slowing down writes meant that the Java REST services threads were being occupied waiting to be able to write the data, which meant there was less threads being able to handle new requests coming in, meaning the outside crawler systems had to slow down. We kind of had a system propagating backpressure without even realizing it. So, as with all things, life gets more complicated. The system is what we previously described was not necessarily the complete system. Really, inside of our four walls, it's more complicated, where we add on a processing component later on that takes data out of that NoSQL system, does a lot of complicated heavy lifting, aggregations, joins, selects, handling reference data or retrieving ad hoc context to be able to build up. So a lot of complicated work is happening. So this is kind of now the complete picture. And we had an expected service level agreement, or SLO or SLI, whether it's officially a contract or not, doesn't really matter, but we had an expectation that we needed to be able to process the data in a certain amount of time through the entire system. And similar to the simple system we were talking about, we had the same cases occur. Sudden spikes of data coming in caused us to violate our max supported throughput and suddenly start to fail or could become behind. And we would do things like we would expect. We would start to scale out when we could, increasing our max level, being able to handle the new data coming in. But in the time it took us to be able to scale out, and maybe only being able to scale out to the point we're keeping up with incoming code, we also developed a backlog, a number of messages that we had to actually be able to process through. We were only keeping up with the new messages coming in. We were not able to eat through that backlog. And so, since it's a FIFO type system, we had to be able to process this backlog before we were able to process the new messages and get ourselves back within that expected processing time. And so, an executive posed a question to a group of individuals. How do we actually handle this situation? A lot of ideas were bandied around, but someone threw out the concept of, let's add backpressure. And this was an intriguing idea to me. I was trying to figure out, what does adding backpressure mean? Where would we add it? Where does it make sense? What would it be telling, and who should be concerned about the backpressure? Now, if we think of it as a complete system, we would have backpressure at the very extremes. So no data would come in, and handle it all the way to the end to make sure everything flowed through effectively. And what would we do in this case? In actuality, probably someone uttered those horrible words that we hate hearing about because it oversimplifies the problem more than we expect. Someone probably iterated the words, "Why don't you just rate limit the uploads?" And that's an idea. What it actually means in this case is that we would say that system X cannot upload more than Y requests per second. And if we look at across the industry, we actually see that it's a common pattern. AWS and Google Cloud Platform do it with a lot of their systems like Kinesis or PubSub, trying to stop a misbehaving client from being able to take down the system. They also do it for monetary reasons, hoping to charge more when you actually want to go above a rate. And it actually is probably a good practice. Most systems probably need to have some form of rate limiting to make sure that a client can't misbehave or take down your system. But as a whole, it's not actually a great, honest, and pure solution. There are downsides to it. For one thing is it puts problems on our consumers that they shouldn't necessarily have to deal with. It's our processing infrastructure that's not keeping up, not that they are necessarily doing anything misbehaving or inappropriate. A lot of the actions that happen or cause spikes are typical maintenance things or operations that they would have to deal with. Additionally, it actually leaves spare capacity on the table. You have to set a request per second limit much below what your system can actually handle, meaning you're usually paying for extra capacity that's not actually being used. And probably one of the other reasons is that limiting the max request per second doesn't actually guarantee stability. This might seem unintuitive, but let's look at an example or how this actually proves out with math. Specifically, we can look at Little's Law, which came out in 1954. It was used to describe the flow of customers through a system or into a store being serviced and leave. And it kind of brought up three concepts that are very easy to describe and interact in a single equation. We have L, which is the mean number of requests handled inside the system, or the mean number of customers inside the store. You have lambda, which is the arrival rate, which is how many customers are coming to the store, or how many requests are coming into the system. And you have W, which is the mean transaction time. How long does it take to actually serve and handle that customer? So let's take it through an example. In this case, we're not dealing with computers and we're not dealing with customers. We're dealing with someone who's basically doing paper processing. They get a message, they have to process it, they have to send it on. And in this case, we're actually going to put some constraints. Lambda equals 1, meaning 1 request per clock tick. W equals 2, meaning that it'll take 2 clock ticks to actually process the message on average. And L, we don't know because it's too complicated for us to calculate right now. So at clock tick 0, there's no messages in the system. At clock tick 1, we get 1 message in. Clock tick 2, another message, but nothing's left yet because we haven't passed the mean transaction time. And at clock tick 3, a message actually leaves. And then at clock tick 4, another one comes. And now we kind of have a reasonable sample size, and we feel comfortable pulling out that hard mental math, which is 1 times 2 equals 2. There's 2 concurrent messages inside the system. If things get busier, say that we actually get 5 messages per clock tick, we adjust the calculations and we see that we should have 10 in the system at a time. So on the next clock tick, we get 5 more messages and 1 leaves. So we're at 6 total in the system. And then 5 more arrive, 1 more leaves, and then eventually we're done processing 2 clock ticks, that first group of 5, and then 5 will go out the door. And we kind of see that the system is in balance. And it's interesting is that the simple idea works really well when describing a single component, but it also actually works when you're talking about systems within inside of systems. So how do actually your components play together to describe a large holistic solution? And the math still actually works. But we went down this path talking specifically about how it relates to request limiting. And if we look at this equation and how it goes with request limiting, we need to look at the different aspects. Specifically, L is the capacity of our entire system. More than likely, that is not an infinite resource. You have memory constraints, disk space, network, connection pools, etc., that are going to limit the number of things that can be inside of your system. So it has an upper bounds. We do not want it to go on a trend to infinity. Rate limiting basically is talking about that lambda aspect. It's trying to constrain or fix that specific point. But we still have another term that can change over time, which is W, which is the mean transaction time, how long it actually takes to process. Now, it's true if we kind of can control the number of messages coming into the system, we can hopefully help to control the transaction time. But there's lots of different factors that could play into this. Failures of node, maintenance periods, reduced capacity, all of which suddenly change your W values to continue to increase, which would then cause your L values to increase even though you're fixing the requests per second. So therefore, just limiting that one factor doesn't mean or doesn't guarantee you're going to have stability. So if we look back at this entire picture, rate limiting is not necessarily the only solution that we should have. We might implement it, like I said, for safety to prevent misbehaving clients, but we still have to build out to solve the system to be stable. Now, I indicated earlier that the processing component was actually where most of the work was being done. The heavy computations, a lot of the delay was occurring. A lot of the upstream systems were able to push data through, could scale out a little bit linearly, or scale at a larger rate than that processing could. But so if we have to be able to think about how we're doing backpressure in this processing, let's quickly glance through how backpressure might work throughout the other parts of the system. The HTTP services are actually, there's a lot of idiomatic ways throughout the industry to do backpressure in that system. We talked about rate limiting, but there's actually a lot of libraries and a lot of methodologies that you could think about as well. Bulkheading and concurrency limits are both things that will kind of constrain the failure domain or the isolating someone's impact on the system in a way that would stop them from being able to hurt the system as a whole. The queuing mechanism is actually very interesting and plays into the system as well. In this case, we chose an open source queuing mechanism, more of a distributed log than an actual queue, but it was actually designed not to care at all. It didn't want to know it wanted no interaction between the production system and the consumer side. So it actually was intentionally a seam to separate those concerns out. And it does have a few upper boundaries, specifically things like the amount of disk space it could use at a certain time, but it's way higher than anything we've been dealing with. And they did eventually, in newer iterations, implement things like request quotas to make sure the system can't be taken down. The NoSQL systems are actually very similar and behave similarly to some of our RDBMS systems, where you have flow control. So if I can't replicate data efficiently, I'm going to pause writes into the system, and that'll inherently give a backpressure for stability. It might have max connection limits, stopping a system from being able to beat the daylights out of it. Or priority connection pooling, meaning I'm going to be able to protect what resources I need to keep the system up, no matter the number of requests coming in. So that leaves us with backpressure throughout the entire system, but what does it actually mean in the processing component? And more specifically, what is that backpressure actually protecting? And if we're still kind of driving from the original statement of can we protect this system to handle our agreement and keep up, would it actually help was kind of the question that sprung to my mind. And for us to look at this, I want to look across a number of the common stream processing engines in the industry, Apache Flink, Kafka Streams, Storm, and Apache Spark, and wanted to try and figure out how they implement backpressure. And you could Google pretty much stream processing XYZ and backpressure, and you're going to find lots of articles about everything. So besides these, there's plenty of proprietary ones or other additional open source ones that talk about backpressure. And each one kind of solves it in an interesting and different way. Kafka Streams takes a basic approach of we don't have a mechanism for backpressure, we don't got one, and we don't need one. And the reason being is it's a very simplistic system that basically constrains the value of L from Little's law to a value of 1 at all times. It'll take a message, process that message, and then send it on before it ever starts trying to get more data. Essentially, it's trying to protect itself by constraining that single L value. If the downstream system and persistence is slow, it'll take a little bit more time, and that's okay. It doesn't have to worry about that system falling over. Apache Spark actually has a number of streaming implementations, but specifically the structured streaming and its direct approach in the Apache streaming try to solve this simply by dealing with the lambda value, saying I'm going to do the same request rate limiting that you would maybe do with a normal HTTP server. So it actually falls victim to the same problems we talked about, where if you're not able to process successfully in a fixed amount of time, eventually your system is going to become unstable and fall over. The other systems, like Apache Flink and Apache Storm, actually try to constrain the L value. They want to make sure that you never grow beyond a certain number of messages in the system at a single time. Apache Spark streaming, as I mentioned, or Apache Spark has a lot of different implementations of streaming, and one of their other implementations actually takes into account two different factors. Specifically, it tries to do rate limiting, but basing upon the fact of how long it takes for you to actually process. So it will dynamically change the rate limiting based off of how it behaves. So how does it actually work in the systems? So Apache Storm looks like this. You build a topology of processing based off of spouts, which take messages and send it into the system, and bolts, which actually do the processing and the persistence. Storm gives you exactly once, it gives you guaranteed message passing or message processing. And it does this through a series of acts, where once the message gets successfully through the entire system, it tells the spout it was able to do it successfully, and therefore it doesn't fail. And it must do this in a configured timeout period. So Storm's first initial pass at Backpressure was to have a configured max spout pending. So this is the number of messages that spout is allowed to send into the system. Or how many, and in an aggregate, it's how many messages are in flight. And to be able to arrive at that value, you have to do some interesting calculations. You have to base it on the number of spouts in your system, the number of bolts in your system, because you want to keep those as busy as possible, because that'll give you the highest throughput and the lowest latency. You have to worry about the available resources, making sure you don't go and send more messages than memory you have available. You have to worry about the time it actually takes to actually do the processing. And more importantly, you have to be able to do all of that before the timeout period, or else it's considered a failure and it'll start sending more messages into the system. And what's interesting is the solution is actually very reactive to feedback. If I'm having trouble writing, it'll slow the system down, and it'll make sure it's kind of give it a little bit more safety and stability. But it is hard to tune. While I said calculate, what I probably really meant was experiment and trial and error and hope you can handle the failures. And it's actually easy to tune for instability. That initial case where we tipped over the NoSQL and made it unhealthy, that was because we jacked this thing up as high as we could to force as much data into that NoSQL system, eventually causing everything to cascade and fail. Storm did implement a new backpressure mechanism. And in this case, what they did was they tried to constrain L based off of a receive buffer. The receive buffer has a low watermark and a high watermark. The moment that your buffer gets filled above that high watermark, a background thread gets spawned off telling Zookeeper that, hey, we should be implementing backpressure, which tells the spout to stop sending messages. And then it stops sending messages up until the point that the receive buffer gets below the low watermark. What's actually interesting about this implementation is that it does it's easier to tune, but it's not really production ready. Because shortly after it was rolled out, they had another release which turned it off by default. And what's actually probably very intuitive when you look at it in this case is it actually caused other systems to start to fail. They were not expecting backpressure to be triggered as often as frequently it was, so they actually beat the daylights out of Zookeeper, which is an important part of the infrastructure for it to even be able to run. So while they were trying to make Storm stable, they undermined any stability they were kind of getting. Apache Flink takes once again another approach similar to constraining the value of L. In this case, you have sources and sinks. You kind of describe your processing as joins and aggregations and groupings. And based off of that, it will break it down into a series of tasks. And the data will flow from the source through the tasks until being persisted out to the final sink. Flink advertises and sells itself by backpressure being a native part of its actual architecture. And the way it actually works is that every single task has a fixed buffer pool. When data comes in, it gets written into a buffer that gets taken out of the pool. The data will slowly fill that pool until it's full, and then processing will start. More data comes in, we take another buffer out, we start filling it up, and we're continuing to do processing. And then eventually more data comes in, more processing is happening, and eventually, once we've exhausted all of the different buffers in that pool, that task inherently cannot receive more data. And that task says, stop telling me what to do. Up until that point, and then eventually, hopefully, the processing actually happens, and then data starts to be freed up. That buffer says, I actually need to send to downstream processing. and I will continue to sit there up until the next component says I've successfully received it. So you kind of can see how this picture would work with many tasks chained together. Once the next task has said I've received it successfully, it goes back in the pool, and now it's eligible to start receiving data. As a whole, what's interesting about this system is it guarantees that some progress is going to happen. It also guarantees that each task will kind of never drown itself, sucking on the fire hose of data flowing into it. And because these tasks are chained together, it guarantees that backpressure will propagate throughout the entire job, and it also means that the max throughput of the entire system is a function of the slowest part of the system. So I mentioned there's a lot of different parts of Apache Spark, especially when it comes to streaming. And we talked a little bit about the direct and the structured streaming as being the rate-limited parts. But now let's talk about the receiver part. This was one of the earlier legacy-type implementations. And taking a little bit step back, a Spark streaming application's goal is to take a constant stream of data and break it up into a series of batches. And these batches are expected to then be processed and emitted at a known configured interval. So I expect to produce this batch every 5 seconds. What's built into this receiver is the concept of a rate limiter. And the rate limiter's goal is that as data is coming into the system, being processed and sent out, it'll measure to see how long it is taking to actually do that processing relative to that batch interval. And specifically, the one that's implementation that's available is what's called a PID rate estimator. A proportional, integral, and derivative is what PID stands for. And the goal of this estimator is to calculate error based off of a set point and measure it against a process value and apply some form of compensation or correction. This isn't a concept that's purely based in computer science. It's actually something that's been around for a long time, used to help boats automatically correct and shift. It's also something that you can intuitively think about if you've ever used cruise control on a car. The way it works is you get that feedback of what we want, what our desired state is versus what our actual state is, and then goes through 3 different functions to then be combined together to actually be the correction that you apply. Each of these components performs a different part of this whole system. The proportional piece actually measures what is the difference or what is the state of our system. So if you set cruise control to be at 65 miles an hour, but your car is only going 60, proportional would say, hey, we need to speed it up 5 miles per hour. The integral component kind of takes a historical trend, saying that yes, right now the system is kind of trending in this direction, we need to speed up, but we probably need to go a little bit longer and past the point of once we hit exactly 65 miles an hour, because perhaps we're actually going up a hill, keep applying that force. And then of course there's the derivative term, which tries to dampen this, because what we don't want is wild swings up and down trying to hit the actual desired end state. Can you imagine how nauseated and carsick you would be if you constantly were swinging above and below 65 miles an hour, wild giant swings? And we don't want our systems to behave this way either, because then we're almost forcing ourselves into a point of instability. In the case of stream processing in Apache Spark, what we find is that error, or the part that PID is estimating, is the delay time. How much longer are we taking to process the data than the batch interval? Because if we're taking longer than that batch interval, our system is just going to continuously be behind. So they apply compensation by adjusting the rate. Specifically, if delay is really, really high, we're going to put less messages into the system. If delay is really, really low, let's put more messages in the system because we can do more work. So the question then becomes like, which one of these is the best? And there's not really a great and true way of actually doing that measurement. There's a number of concepts that we can think about. Specifically, we can think about them on various spectrums, like are they reactive? Are they responding to changes in the environment? Or are they kind of fixed, bullheaded, and then force their way through? Are they simple and easy to reason about, or are they very complex? And also, are they stable? And so if we kind of ad hoc plot these on various spectrums, we see that they look like this, where Flink is highly reactive. If the system as a whole at any point slows down, it will slow down appropriately. Things like Kafka streams I plotted in the middle because it doesn't really care. It's going to slow down if it has to slow down. It's going to go fast if it can go fast. But it's really not going to react one way or the other. It's just going to kind of do its thing. And Spark and Storm do their things as well. On the case of simple and complex, Kafka streams is kind of very much on the simple, as we talked about. And we see that things like Storm and Flink are maybe slightly on the more complex side because you have to do a lot of complicated math and tuning to hopefully get it right. And there's a lot of interesting feedback that's coming through it. And if we kind of look on the stability, we see that systems like Flink and Kafka Streams will be stable, and other systems will kind of have some stability, but they're really just kind of giving you a false set of hope because they have the high potential to actually fall over in spectacular ways. So if we go back to the original set of questions I presented, what does it actually mean and what is backpressure protecting in a processing engine? We see that it's doing so, what it's actually protecting is that processing engine itself, guaranteeing that it's going to be available and able to do work. But it also is to a little bit helping the downstream system as well. If I can't push data into it fast enough, I will then propagate and send that message back. But if we look at the overarching question of will backpressure in a processing system actually help, the answer is not quite as clear. What we actually find is that when we look at all the components individually, they all have some form of backpressure which will help and protect themselves. But right now, our mechanisms are independent. And one of the interesting things is that they're all independent because we actually implemented that queuing mechanism in the middle that potentially doesn't care about one side versus the other. So we did a good thing by actually protecting our consumers from having to care about the problem, but we also kind of implemented a case where there was no constant feedback of backpressure throughout the entire system. So we find ourselves back in this situation. We still have that giant backlog that we have to get through in a reasonable amount of time to be able to make our consumers happy. And we find that backpressure will help maintain our system and stick around and make sure it's reliable and standing up to the onslaught. But we need to still actually recover that SLA. We have to get our processing back within scope. And that brings up kind of the next way to deal with handling the pressure, which is what's called load shedding. And this is basically an idea that you ignore some of the requests because it is better to serve some of your consumers and their clients' needs than to fail all of them. And inherently, you probably felt that was a gut punch. You're thinking to yourself, we can't drop our important data. Now, I'm not proposing that by any stretch of the imagination, but we have to do something. It shouldn't be your first choice to load shed, but it more than likely has to be a choice. Now, I might be considered pessimistic. I hope that I'm more in the realm of realistic. But more than likely, if your system is becoming adopted and becoming more widespread, you're going to encounter load expectations that are beyond what you actually can handle. So you need to think about how to actually do load shedding in a safely and reliable manner. And it's not an action or a process or a workflow that you want to be coming up with late at when a problem's actually occurring, or at 6 o'clock on a Friday when you really just want to go home and have a peaceful weekend. And when you're trying to come up with this process, you need to think about how to minimize the impact. You don't want to just completely shut down the whole system. You want to isolate it to where it actually makes the most sense so that you don't affect more than is actually necessary. Does it actually affect all consumers or maybe just a few? So in this case, we need to safely shed the backlog. We're actually able to do that in the distributed systems world because we have a lot of tools, not just from a stream processing standpoint, but we have batch processing. We can basically say, you know what? Let's cut the backlog, let's reset from all new data coming in, and let's batch process all of the data that was queued up within the system. Now, it's true that data will not be available within that expected time frame, but new data will suddenly be able to be available and visible throughout the system within the expected time frame. And it's probably easier, and we can do it with a higher throughput, batch process all of that historical data. Now, it might take many hours, but still probably in aggregate, it's less time than it would take to actually try to churn through that backlog, or fiddle with the tuning to hopefully get high enough to then churn through it and not tip over or cause problems throughout the rest of the system. But then becomes a question of, how do we detect the need for load shedding? Often, we rely on our gut. We look at the monitoring and the measurements and think, it's probably not going to work. And unfortunately, that's not a good mechanism. As we talked about or heard in earlier presentations, the difference between judgment and intuition. We don't want to necessarily have to rely on our intuition. It'd be great to have something that's empirical and mathematical that will tell us, you know what, it's time to make this clear decision. And when you research backpressure and math, you get a lot of interesting hits. And one of the things you kind of will quickly stumble upon is what's called Lyapunov's drift, or Lyapunov functions, Lyapunov optimization, something that's actually baked into things like backpressure routing throughout an entire network. Now, what is it? It's clear as day, based off of these easily readable words that everyone understands. You probably only need about 20 to 30 more YouTube videos that'll tell you how to design the function and get it actually working, and then you'll be able to easily calculate on the fly when you should do load shedding. But that's a lot of ifs and a lot of things to deal with when there's actually a lot simpler tools that we can think about in our system. Specifically, let's go back to the math that we can easily do in our head. Let's go back to Little's law. And if we think about it, if we want our system to be able to be performant, and we think about the attributes of Little's law, what we see that W value needs to be less than or equal to our service level agreement, or we have no hope of ever actually being able to satisfy that. Additionally, if we were going to be measuring and monitoring the system, we see that L needs to either be trending in a downward value or a steady state. If either of those are not true, our system is more than likely unstable. So these are kind of just some quick tests that we could think about for how our system is behaving to detect whether or not we need to do load shedding. And if we do a little bit of math, we find that the number of messages in the system divided by the number of messages coming in, and if that's greater than our service level agreement, our system's more than likely unstable and headed in a bad trend. And both of these are probably very easy to measure in your system, whether you have it as requests coming in at the HTTP layer or a backlog measuring and alarming off of. All of those things are measurable and detectable, and more than likely you can probably do an alarm based on them. And this whole system as a whole will start to see things like the L value trending upward. And if this is happening, you're headed for a bad time and a bad weekend or a bad on-call time. So hopefully I've not filled everybody with doom and gloom. This is a manageable system. We just need to think about it in a lot of different aspects and use a lot of different tools. There's not a single fix. It's not just as simple as adding this one feature or why don't you just doing that. It's built upon you coming up with a plan and interacting and interweaving all of these different components. It's built upon the idea that you've built out monitoring from the start as a first-class feature of your system. Believe me, it is a lot easier to troubleshoot an issue if you know how to answer the questions than for you to try to figure out how to answer the questions and then figure out how to fix the problem. So try to think about those problems ahead of time and measure for them and how they're going to come up. We should scale out, but more importantly, we should scale out and do it safely. We shouldn't say, you know what, I can go full throttle, I can have a good time, but I'm going to completely hurt this other part of the system. We need to think about the entire system as a whole and about scaling efficiently. Backpressure should be something we think about implementing. We need to make sure we know where it is in our system, what value it's providing, what it's protecting. We need to think about, hey, should we actually add a mechanism or enable a feature and functionality to use this to our advantage for the safety of the entire system? And load shedding. I still maintain it's a when question, not an if question. And you need to come up with a plan and practice that plan and think through it. It'll make your life a lot easier and a lot less stressful. And overall, we need to avoid the L-ball process. Because while it makes for great comedy and entertainment, it's not how we should be running our systems. Because we don't want to be just bragging about or joking about how spectacularly we killed our system. We want to be responsive and handle it to keep our consumers happy. I'd like to give a quick shout out to some of the folks in that initial conversation where we had about how do we actually handle this. And here's a set of references. One of those is the I Love Lucy skit, so look for that. And please leave some feedback. Thank you very much for your time.